Hi everyone, I hope this video format works out better. I'm going to go through the questions that I meant to go through during the practice session, so let's just get started. So question 6-111 is a completely reversible heat pump has a coefficient of performance of 1.6 and a sink temperature of 300 degrees Kelvin. Calculate the temperature of the source and the rate of heat transfer to the sink when 1.5 kilowatts of power is supplied to this heat pump. Alright, so I will first write out what we want, and that is the temperature of the source. So we want TL, and then for part B we will also want the Q dot H. So at the top we have the sink, which we were given as having a temperature of 300 Kelvin. And then, sorry for the little arrow, but then this is going to be Q dot H. And dot is the rate of heat transfer. It's not the total heat transfer, but if you can recall that so heat transfer is Q, and Q is in terms of joules, or kilojoules. So if we divide kilojoules by seconds, we get kilowatts. So Q dot is equal to kilowatts, which is really just kilojoules per second. Then going back, we have the source, which is drawn below the heat pump, and we have yet to figure out the temperature of that. We'll just write TL right now, and that has an arrow of heat transfer, Q dot L. This one up here has a Q dot H. Just to be more specific, we have to give it that notation. And then, in addition, in this problem, we have work coming into the system. We have 1.5 kilowatts of work going into the system right here. 1.5 kilowatts, and that is with the notation W dot net. I know, sorry about the reflection there, but we have a completely reversible heat pump, so that gives us enough information to find equations to use. So the main equation that we have is that, I'll write this in blue, we have that COP of the heat pump is equal to 1 divided by 1 minus QL over QH. So that is just an equation that is super important to know. It is on page 280 of the textbook, if you guys want to reference that. But another important consideration is that because this is a completely reversible heat pump, we find that there is a thermodynamic temperature scale, I believe it's called, but we can basically solve this equation as if QH divided by QL is equal to TH over TL. Basically, if the system is completely reversible, those ratios will equal, and I'm going to specify that this is only if the system is reversible. Alright, so with those known, we can then find the low temperature, the temperature of the source, by just plugging this part into here. So we can do well, I want to do some algebra first before plugging in some values. So we'll do COP is equal to 1 divided by 1 minus, and then we have TL over TH. And we can rearrange the equation, do COP times 1 minus TL over TH is equal to 1. I'm going to continue on the right side. Then we are left with 1 minus TL over TH is equal to 1 over COP. I'm going to combine some steps. So now we have TL is equal to T is equal to TH times 1 minus 1 over COP. So now with this equation, we can just plug in our givens. We can find that TL is equal to 300 degrees Kelvin, and we don't need to convert since it was already given in Kelvin. 1 minus 1 divided by 1.6. And then with that, we just get the value of TL is equal to 112.5 Kelvin. Now that we have part A, we need to move on to part B. Q dot H, the rate of heat transfer to the sink. So to do that, we can just go all the way back to this equation, but we will also need an additional equation, which is kind of more the definition of the coefficient of performance, the COP. So we have that the COP of a heat pump is equal to QH divided by the net work in. So in this problem, we want the rate. So we can technically divide both the numerator and the denominator by time. So we can do 1 over seconds, and then 1 over seconds. And then this would give us the rate form of this equation. So instead of this, we can just put dots to notate that we are, in fact, using this equation in the rate form. All right. So, because we're just looking for this Q dot H, and we know both of those, we can then just so because we know both the network in and the coefficient of performance, we can just find that Q dot H is equal to the COP times work net in, and then plugging in the values that we have, that's 1.6 times 1.5, which leaves us with 2.4. And I forgot to add units. This 1.5 is in units of kilowatts. The coefficient of performance is unitless. So that is 2.4 kilowatts is equal to Q dot, the rate of heat transfer to the sink.